Assalamualaikum and good day everyone. Okay, in previous lecture for week 3, which is about the flux density and divergence theorem. So far we have learned about the introduction to the electric flux density, we also learned about flux, and we also learned about application of Gauss law. Okay, to calculate the electric field intensity for symmetric charge distribution. Okay, now moving forwards, we will learn about divergent concept and the divergent theorem. You see, I have covered before about the del dot d. Okay, this is divergence. Okay, del dot a vector is a divergence, and I have covered briefly in my previous YouTube videos, which is the week 1 del operator part 2. Okay, you can have a look at it again so that I won't be repeating the same thing. Okay, also from the Sadiko book you can find about this, if I'm not mistaken, at page 77 of section 3.5. Now, without further ado, okay, let's imagine that we have a line charge here. Then you have electric flux density of D, and you have a point here. So let's say you want to evaluate the divergence at the point here. Okay, so if you notice, this divergence is actually coordinate dependent, so you need to solve using either of the three coordinates available, which are your Cartesian, cylindrical, and also spherical. Okay, so this equation you can find from Sadiko textbook, page 79, equation 3.29 for the divergence A, that using Cartesian system, divergence of vector A for using the cylindrical system, and divergence of A for the one that using the spherical system. So Maxwell equation del dot electric flux density describe that the divergence of D at a given point, okay, is the outward electric flux, okay, outward electric flux per unit volume as the volume shrink about the point, okay, and this is equivalent to volume charge density. Okay, so this is actually your Maxwell first equation for, in this case, for electrostatic. Then what is divergence theorem? Divergence theorem states that the total outward flux of a vector field, for example, vector A, through the closed surface S is the same as the volume integral of the divergence A. So the total outward flux of a vector field, for example, vector A, for example, through the closed surface S is the same as the volume integral or the divergence of A. Okay, you can see this is actually the closed surface. So this is your vector. This is your vector as well. And this is your vector. Okay. So this will result in scalar, and this is result in scalar. Okay, so we will try later on, or you can try on your own first, okay? Because this is one of the example in the handout that I will share later on, okay? One of the exercise. So determine the charge density at point P at point P -1, 0, 3 if the electric flux density is equivalent to y square plus z unit vector x, unit direction x, plus 4xy unit direction y, plus xz unit direction z, coulomb per meter square. Then calculate the flux passing through the cube 0 x 1 0 y 1 0 z 1. Okay, you can try yourself first. And then how you practice using let's say you get direct question about find the divergence at the origins and something like that, or at a point. You can solve just like what I give in the previous YouTube videos. Okay, this one. Okay, so I hopefully everything is okay, and inshallah we'll see you again in the next lecture. Thank you.